Hello, this is the second lecture of the course on advanced electric drives. In the last lecture, we are discussing about the generalized theory of electric machine, in which we have a common framework for analyzing all sort of rotating electrical machines. Now, we also discussed about the Cron's primitive machine model. To repeat that, I can show that once again. We have discussed already Cron's primitive machine model, which was given by a scientist called Cron in early 20th century. Now, if you see this particular model, the Cron primitive machine model, what we have here, we have a rotor structure and we have the stator. And in the stator, we have two different axes. One is the D axis. This is called the D axis, and this is known as the quadrature axis or Q axis. And we have two different windings, one set of windings in the D axis and the other set of windings in the Q axis. For example, in the D axis we have our winding in the stator. This is basically the stator winding, which is stationary, not rotating, and this is the rotor which is rotating. This is the rotor, and the rotor is rotating in the clockwise direction. So, the direction of rotation is clockwise at the speed of omega r. This is the speed of the rotor. Similarly, in the rotor winding, we have a winding in the rotor in the D axis, and in the Q axis we have a stator winding, and in the Q axis rotor we have a rotor winding. So, we have shown the actual machine as a two axis machine, where we have two well defined axes, one in the D axis and one in the Q axis. The objective is this, that it may be a AC machine, it may be a DC machine. The effect of a AC machine or a DC machine can be well understood or can be simulated by a two axis model. It is sufficient to have two orthogonal axes. Two orthogonal axis means two axes should be perpendicular to each other. One is the D axis, another one is the Q axis. Now, please remember that this machine that we are talking about, the Cron's primitive machine, is essentially a hypothetical machine. It does not exist in reality. It is for our own understanding, for our own convenience, we have taken the help of this machine to simulate an actual machine. So, in this case we have two different axes. In the D axis we have the stator winding, and this we call to be the DS winding, and we can have applied voltage here, and the applied voltage is VDS. D stands for the direct axis and S stands for the stator, and this is my terminal marking. We can show this as dot, and this is the current that is entering into the winding, and this current is IDS. Similarly, in the rotor I can have applied voltage, and the applied voltage here is VDR, and this is my dot here. These two windings are coupled. The D axis stator is coupled with the D axis rotor. These two are the coupled windings. The D axis stator is coupled with the D axis rotor, and this dot shows the positive terminal. Here the current in the rotor is entering the rotor, and this current is IDR. Similarly, in the Q axis I have the terminal marking here. I can show this by a triangle, a small triangle here. Similarly, I can show this by a small triangle, indicating that these two terminals are similar. In the Q axis, similarly I can have applied voltage. I can have applied voltage here in the Q axis, and this voltage terminal is positive, this is negative, and I can call this voltage as VQS. And the current in the Q axis winding is entering this terminal, and this current can be IQS. Similarly, in the Q axis rotor, I can have applied voltage. This voltage is plus here and minus here, and this is VQR, and this current in the rotor Q axis winding is entering the triangle terminal, and this is IQR. So I have these two windings, these two sets of windings, and they are orthogonal to each other. It means the D axis stator is not coupled with the Q axis stator. Similarly, the Q axis rotor is not coupled with the D axis stator. They are orthogonal windings. Now in this case, what I can do here, I can write down the voltage equations. Now when I write down the voltage equations, I can start with the D axis stator winding, VDS. This winding is a stationary winding. So I can just write down the voltage as RDS is the resistance of the winding into IDS is the current flowing through the winding plus the statically induced EMF, because the stationary winding can have a statically induced EMF, and VDS is a stationary winding in the stator. Unless the winding is rotating, there is no rotationally induced EMF. So I can just say that VDS is RDS R IDS, the resistance drop, plus P psi ds, the statically induced EMF in the D axis stator. In a similar way, I can write down the Q axis voltage equation in the stator, that's equal to RQS IQS plus P psi QS, and this winding is also stationary, and hence there is no rotationally induced EMF. I just have a statically induced EMF in the Q axis, that is P psi QS, and the psi are the flux linkages. Psi ds is a flux linkage in the D axis stator, psi QS is a flux linkage in the Q axis stator. Coming to the rotor winding, when I write down the equation for VDR, the D axis rotor winding, I will have both statically induced EMF and rotationally induced EMF, because the rotor is rotating. So I can have a component of EMF which is coming due to the rotation of the rotor, and that EMF is called the rotationally induced EMF. So I can just write down the equation for the D axis rotor, that's equal to RDR IDR is the resistance drop in the D axis rotor plus P psi dr. P psi dr, P is the derivative term, that is d by dt. This is the differentiation of the flux with respect to time. P is equal to d by dt. It's a derivative operator. So I can just write down VDR equal to RDR IQR plus P psi QR. This is a statically induced EMF, and here I will have a rotationally induced EMF, but I don't know its sign. But I know that the rotationally induced EMF, as we have already seen in the last lecture, it appears in the quadrature axis, in the orthogonal axis. So I can just write down it is omega r into psi QR. It means the rotationally induced EMF in the D axis is due to the Q axis flux. It's something similar to a DC machine. In the DC machine, what we have here, we have the armature, and this is our armature axis, and we have the field winding here. This is the schematic diagram of a DC machine, and the voltage that is appearing in the armature of a DC machine due to its rotation, omega r, is because of the flux in the D axis produced by the field winding. The field winding and the armature winding are orthogonal to each other, in the sense that the field axis here and the armature brass axis are orthogonal to each other, and hence the induced EMF in the Q axis rotor is due to the D axis stator. The same thing is here appearing here, that the voltage equation in the d axis rotor will have a rotationally induced EMF due to the q axis flux. However, we will find out the polarity of the rotationally induced EMF little later. Similarly, the voltage induced in the q axis rotor is given by RQR, IQR. This has to be IDR. RQR, IQR plus piece IQR. Again, I don't know the polarity of the rotationally induced EMF, so we'll have plus minus omega r psi dr. Here again, the rotationally induced EMF in the q axis is appearing because of the flux in the d axis, that is omega r into psi dr. All right. Now, what are the various fluxes? We have to define the various fluxes. What are these? Psi ds, psi qs, psi dr, and psi qr. They are the flux linkages in the stator and the rotors. Now, psi ds is equal to LDS IDS plus MD into IDR. LDS is the self inductance of the d axis stator. MD is the mutual between the d axis stator and d axis rotor. Let us go back to the previous slide. Now, the self inductance of the d axis stator is LDS, and the mutual between the d axis stator and d axis rotor is MD. Similarly, the self inductance of the d axis rotor is LDR, and the self inductance of the q axis stator is LQS. Self inductance of the q axis rotor is LQR, and the mutual between the q axis stator and q axis rotor is MQ. So, psi qs is produced due to the current in the d axis stator and the current in the d axis rotor, and hence we can write down psi ds is equal to LDS IDS plus LD MD into IDR. In a similar way, I can write down the flux linkage in the q axis stator, that is LQS IQS, flux in the q axis stator due to its own current, and the flux in the q axis stator due to the current in the q axis rotor, MQ into IQR. In a similar fashion, I can write down psi dr. Psi dr is equal to LDR IDR plus MD IDS, and psi qr is equal to LQR IQR plus MQ into IQS. So, these are the flux linkages. In stator and rotor windings. So, let us try to see, actually we have the voltage equation VDS, VQS, VDR and VQR, and what we have to find out right now is the direction of the rotationally induced EMF. Now, we have already seen that the rotationally induced EMF appears due to the rotation of the rotor, and the rotationally induced EMF also appear in the quadrature axis. It means the rotationally induced EMF in the d axis rotor is produced due to the flux in the q axis rotor. Similarly, the rotationally induced EMF in the q axis rotor is produced due to the flux in the d axis rotor. So, let us try to see how the rotationally induced EMF is produced and what is the direction of the rotationally induced EMF. Now, we will take the first instance, the determination of the sign of rotationally induced EMF in the rotor. Determination of the sign of the rotational induced EMF in the rotor. So, if you see the rotor, let us say that initially we will take the effect of q axis flux on d axis rotor winding. So, we have the rotor winding here, and what we are trying to find out the effect of q axis flux. The q axis flux is here. This is the q axis, and this is linking the rotor. So, I will call this to be psi q r, and I am trying to find out the effect of the q axis flux on the d axis rotor winding. Now, the rotor winding, as we have already seen, that although we have the rotor windings dr and qr, they are called pseudo stationary winding. They are something similar to the windings of a DC machine. So, I can replace the rotor windings by armature winding having two brushes in the same axis. So, this is the d axis winding, and this is something like a DC machine winding, which are called pseudo stationary winding. So, we can have the conductors like this, like a DC machine rotor. So, these are the conductors, cross section of the conductors. So, we have the cross section of the conductors like this here, and the rotation as per the convention is in the clockwise direction. So, this is the direction of rotation. So, we have omega r. Now, we know that whenever a conductor is rotating, if you want to find out the direction of the induced EMF, you have to take the help of the Fleming's right hand principle. The Fleming's right hand principle says that if the thumb shows the direction of motion of the conductor, if the index finger shows the direction of the flux, then the middle finger will show the direction of the induced EMF. The same principle we can apply here. We have a cross section of the machine in which we have the cross section of the conductors are shown here, and in this case we are interested to find out what is the direction of the induced EMF. We can apply the Fleming's right hand principle. If you see, this is the direction of flux here. The flux is radially outward. As per the convention, the flux is radially outwards, and the thumb shows the direction of the motion of the conductors, and hence the middle finger is coming out. That is the direction of the induced EMF. So, I can show that the induced EMF in the upper half of the conductors will be dot. So, I can show them as dot. This is the induced EMF that I am showing coming out of the plane of the slide. Now, similarly, in the lower half or the bottom half, I can find out the direction of induced EMF, that is cross. So, one half of the conductors are carrying dot current that is coming out of the plane of the slide, and the other half of the conductors are carrying cross current, that is the induced EMF is going into the plane of the slide. Now, let us assume that the current and the induced EMF are in phase. If you assume that if the currents and the induced EMF are in phase, it means the currents are being produced by the induced EMF. So, if you assume that, we can assume that the current are in phase with the induced EMF. So, if you assume that the currents are also in the same phase that of the induced EMF, we can find out the flux produced by the current carrying conductors in this particular structure. We can apply Ampere thumb rule. You can see that the Ampere thumb rule says that if the thumb shows the direction of the current, the finger encircling the thumb would show the direction of flux linkage. So, we can have the same principle here. In the upper half of the conductors, we can have the flux linkage like this. It is encircling the conductor according to Ampere thumb rule. Similarly, in the bottom half, if you see in the bottom half, the thumb will be the direction of the induced EMF and the current, and the fingers would show the flux linkage, the pattern of the flux linkage. So we can show that this is the direction of the flux linkages. Okay, and the net flux linkage we can see is coming, is in this direction due to the flux in the q axis. We have the currents producing fluxes in the d axis in this particular fashion. Now this is a positive flux as per the convention. The flux which is radially outward is a positive flux. So it means the rotationally induced EMF in the d axis due to the q axis flux is producing a positive flux and a positive current. It means the rotationally induced EMF is helping the applied voltage. So we can say here that the rotationally induced EMF in the d axis rotor due to q axis flux is helping the applied voltage or the induced EMF is positive with respect to the applied voltage. So we can say that if you write down the equation for the rotor, we can say that VDR is the rotor applied voltage in the d axis, and we wrote the equation that it is equal to IDR RDR, the resistive drop, plus P psi dr is the statically induced EMF, and we had a confusion about the sign. We didn't know whether the sign of the rotationally induced EMF would be positive or negative. As per this analysis, we have shown that the rotationally induced EMF will be helping the applied voltage. Helping means it is plus omega r psi q r. It means that the sign of the applied voltage and the rotationally induced EMF in the d axis are additive, are in the same sign. And if you take it to the right hand side, the induced EMF, if you take it to the right hand side, what you have here is VDR is equal to IDR RDR plus P psi dr minus of omega r psi q r. So this actually clarifies the sign that here is it has to be negative. In the right hand side, if you take a positive thing from the left hand side to right hand side, the sign changes, and hence we have minus omega r into psi q r. Similarly, we can find out the effect of the d axis flux on the q axis rotor winding. Effect of d axis flux on the q axis rotor winding. We can again draw the picture of the rotor. So we can show this as a rotor, and here we are interested to find out the effect of the d axis flux on the q axis rotor winding. The flux is in the d axis, and we can call this to be psi dr, linking the rotor d axis, and we have a winding in the q axis. So the winding in the q axis can be represented by a pseudo stationary winding, which means I can have something similar to a DC machine armature winding having the two brushes in the q axis. And if you take a cross section, we are showing it in terms of a cross section. In the cross section, we can see that the conductor cross sections will be visible. So these are the conductors, and we are seeing the cross section of the conductors across the periphery of the armature, and the rotor is rotating in the clockwise direction as per the convention. So we have the rotation is omega r. Omega r is the speed of the rotor. Now again we can apply the Fleming's right hand principle. Applying the Fleming right hand principle, we can determine the direction of the induced EMF, and the positive induced EMF will inject a positive current. So we can apply the same principle here, that if this is the direction of the field and this is the direction of the motion, the middle finger would be the direction of the induced EMF. So we can do that, and after this we can find the direction of the induced EMF will be dot in the right half from the process. In the opposite half, we will see that the induced EMF direction will be cross, that will be entering into the plane of the slide. And we can again assume that the induced EMF will be circulating a current, and the current and the induced EMF will be in phase. If they are in phase, the induced EMF will be circulating a current, and the current will give rise to a flux linkage. And the current and the flux linkage relationship can be given by Ampere thumb rule, where the thumb show the direction of the current and the fingers will show the direction of the flux linkages. So in a similar fashion, we can say that the flux linkages would be in the following fashion. So these are the flux linkage due to the conductors in the right hand side, and this would be the flux linkage due to the current carrying conductor in the left hand side, and the resultant flux linkage will be in this direction. Okay. So if you say that the resultant direction of the flux linkage, it will be downwards, it will be towards the center of the circle, because this is our d axis. The d axis is in this direction and the q axis is in this direction. This is our q axis. So if I see in terms of the q axis, the flux is entering the circle, entering the center of the circle. It is not outward, but it is inward. So it's a negative flux linkage. So we can conclude here that due to the rotation of the rotor, the rotationally induced EMF in the q axis will be producing current and flux linkage which is negative, which it means that the q axis rotationally induced EMF due to the d axis flux is in opposition to the applied voltage. So we can say here that the rotationally induced EMF in the q axis rotor due to d axis flux opposes the applied voltage or is negative with respect to the applied voltage in q axis. So we can write down the rotor equation in the q axis once again, as we have done for the d axis. We can do that. VQR, that's equal to RQR IQR is the resistive drop, plus P psi QR, and we didn't know the sign of the rotational induced EMF. And as per this analysis, we have seen that the rotational induced EMF is in opposition with the applied voltage. So we can say this is minus of omega r psi dr. So if you simplify this equation, we can say that VQR is equal to RQR IQR plus P psi QR plus omega r psi dr. So we have no ambiguity right now. We have been able to find out as per the convention. We have applied the convention that we have set at the very beginning, and as per the convention, in the q axis it is plus omega r psi QR, in the d axis it is minus omega r psi dr. So we will just write down the equation. Once again, we will say that VDS is equal to RDS IDS plus P psi ds, VQS is equal to RQS IQS plus P psi QS, VDR is equal to RDR IDR plus P psi dr minus omega r psi QR, VQR is equal to RQR IQR plus P psi QR plus omega r psi dr. So these are the four equations that will be essential to simulate the generalized electric machine, which is a Courant primitive machine. But these are in the flux linkages. We have seen that the voltage is expressed as a function of current and flux linkages. So if we replace the flux linkage by current, we can rewrite this equation as follows. Replacing the flux linkages by currents, we can say VDS equal to RDS IDS plus LDS PIDS plus MD PIDR. VQS is equal to RQS IQS plus LQS PIQS plus MQ PIQR, and VDR is equal to RDR IDR plus LDR PIDR plus MD PIDS. This will be minus omega r LQR IQR minus omega r MQ IQS, and VQR is equal to RQR IQR plus LQR PIQR plus MQ PIQS, and then we have the rotational induced EMF plus omega r LDR IDR plus omega r MD IDS. So these four equations are quite important and interesting. This relates the current with the voltages. VDS, VQS, VDR and VQR are the voltages, and the currents are IDS, IQS, IDR and IQR are the currents. So from this we can write down this equation in a matrix form, which will be more interesting, and the equation in the matrix form you don't have to remember, you can just write down by inspection. Let us see how we write this equation in a matrix form. In the matrix form, we can write down this equation as VDS, VQS, VDR and VQR. This is a vector, and then we have a 4 by 4 matrix, and we have to fill up the element of this matrix, and this is IDS, IQS, IDR and IQR. Now we have a 4 by 4 matrix, and we have to find out the elements of this matrix, and this matrix can just be written by inspection without remembering the detailed elements that we wrote little before. So we can say here that this is the self inductance term. So we can have the resistance drop here, RDS plus LDSP. And in the stator we don't have any rotationally induced EMF, and we just have a statically induced EMF, and the coupling between the d axis stator and the d axis rotor will give us MdP. P is a derivative operator, d by dt, and this term you can put comfortably 0 without any second thought. Similarly, in the second row we can have here RQS plus LQSP, and then here we have the coupling between the stator and the rotor in the q axis. So we have MQP here, and these elements will be 0 without any second thought. Similarly, in the rotor equation, this is the d axis rotor, the third row. So we have RDR plus LDRP, and then we have the coupling here MDP, this is the statically induced EMF, LDRP, MDP. Then we have the rotationally induced EMF in the rotor. The rotor is rotating, and due to rotation we have rotationally induced EMF, and those will be coming in the cross axis. It means the q axis flux will produce rotationally induced EMF in the d axis. So here we have minus omega r, also minus omega r here, and this is the rotor. The rotor here will have LQR, and here we have MQ. Similarly, in the q axis rotor we have RQR plus LQRP. The coupling term here is MQP from the stator, and then we have rotational induced EMF, but it will be positive in this case. It's omega r LDR, and here it is omega r MD. So we have a 4 by 4 matrix relating the current and voltages that we can just write down by inspection, by proper understanding, without having to remember each and every element. Okay. Now, if you see this matrix has got the resistance term, has got the inductance term, has the speed term. So we can break up this matrix into 3 different parts. One part containing only the resistance term, the other part containing only the inductance term with P. P is the derivative operator, and the third component consisting of the speed. The speed is omega r here. So we can split this into 3 different matrices. That's equal to, we can have the resistance term here, RDS 0, 0, 0, 0, RQS 0 and 0, 0, 0, RDR 0, 0, 0, 0, RQR. So this is the resistance term. So this matrix, as I was talking, that this can be broken down into a resistance matrix and an inductance matrix having P terms, and a matrix associated with omega r or the speed term. So this is the first component, that is RDS, RQS, RDR, IQR. It's a diagonal matrix, and I will multiply this vector, that is I. And what is I vector? I vector is this vector. Okay, and then I can have the inductance matrix having P terms, and this matrix is LDSP 0, MDP 0, 0, LQSP 0, MQP. Then we have MDP 0, LDRP 0, 0, MQP 0, LQRP. This again multiplied with the current vector, that is I. I is a vector which has got the elements IDS, IQS, IDR, and IQR. And then what is remaining is the matrix with the speed term. Okay, so that we can write down in the following fashion. We can, this is also a 4 by 4 matrix, and what we have, this matrix has got the speed term, so I can take this speed term out, and the first row does not have any speed term. We can put all this equal to 0. Same as the second row, the speed terms are only appearing in the rotor. So I have got minus MQ here, this is 0, this is minus LQR, and then we have MD 0, LDR 0, and then we multiply with the current vector, that is I. So this is a interesting equation, and this equation has got the resistance term, the inductance term having the derivative of the current, and the matrix having the omega r or the speed term. Now if we try to see this equation once again, we can rewrite this equation as follows. The voltage equation that we are writing, the voltage vector V, which has got the components, what is this V? This one is the vector V. So this is the V vector, and this matrix I can call to be the resistive matrix or the resistance matrix, that is R, and this matrix we can call to be this inductance matrix or L. I can take this P term out of this, and the third matrix is the matrix which we can call as G. So we can rewrite the equation once again. V is equal to R into I. This is a capital R I can write here. Plus LPI plus omega R GI. So this is again a representation of the same equation in a different form, having the resistance drop, and then we have the current derivative and the speed EMF or omega R. Now what I will do here, I will pre-multiply this equation by I transpose. I is a column vector, so I can transpose it and pre-multiply. So I can have this matrix here, I transpose R I plus I transpose L Pi plus omega R is a scalar quantity, I transpose G and I. Now if you see in this equation, what is the left hand side? The left hand side of this equation is I transpose into V. Now I transpose into V is the power input to the system, the electrical power input to the system. Now what is I transpose? I transpose is, the left hand side of the equation is as follows. I transpose is IDS, IQS, IDR and IQR, and what is V? V is VDS, VQS, VDR and VQR. Now if you simplify this, you will have VDS IDS, this IDS is multiplied with VDS plus VQS IQS plus VDR IDR plus VQR IQR. As we know that in the Cron's primitive machine model, we have 4 different windings, DS, QS in the stator, DR, QR in the rotor. So the electrical power input to the whole system is VDS IDS, VQS IQS, VDR IDR plus VQR IQR. So that's basically the left hand side of the equation. What about the right hand side? Now if you see the right hand side of equation has got 3 different terms. So if you say the right hand side of this equation, I can call this to be term 1, and this is term 2, and this one is term 3. Now, what about the term 1? The term 1 is I transpose R I. Okay. Now, let us see what is I transpose R I. I transpose is IDS, IQS, IDR and IQR. What is this R? R is the diagonal matrix, RDS, all elements are 0, RQS 0 0, RDR and then RQR, and post multiplied by IDS, IQS, IDR and IQR. Now, if we simplify this equation, what we can pre-multiply and post-multiply these currents with the matrix and then simplify. The result, I will just write down here, the result of this term 1, this is the term 1 is IDS square into RDS plus IQS square RQS plus IDR square RDR plus IQR square RQR. Now, what is this? This equation represents the loss of the system, the electrical loss of the system, I square R loss of the system. So, the term 1 represents the I square R loss of the system. We have assumed that there is no core loss, there is only copper loss. So, these 4 components, IDS square RDS plus IQS square RQS plus IDR square RDR plus IQR square RQR represent the loss of the entire system. Now, what about the second term? The second term is this term. Now, if you see this particular term, we can just see what is this term 2. The term 2 is I transpose L matrix and Pi. I is a vector. Now, if you see, this would represent the power associated with the magnetic field. If you expand this, you will see that this term is the power associated with the magnetic field. Okay. So, this is also the power, and then what about the third term? Third term is I transpose G I into omega R. This is the mechanical output of the system. It is quite natural, because if you see the entire equation, what we can say here is the following, that the electrical input is equal to the system loss plus the power associated with the magnetic field plus the mechanical output. So, this actually is the energy balance of the system, that we are giving some electrical input to the system and some component is wasted as losses, I square R loss. Then some component is stored in the magnetic field that is associated with the self and the mutual inductance, and then the remaining part which is not stored is coming out of the system as a mechanical output. So then if you want to find out the mechanical output and the torque, we have to concentrate on the third term, and the third term is this term. Okay. So we can say here that the P mechanical is equal to omega r I transpose G I, and then that's equal to the torque into the speed. So we can say that that's equal to the electromagnetic torque coming out of the shaft of the machine, Te into omega Rm. Omega Rm is the mechanical speed. Now if you want to find out the torque is equal to P mech by omega Rm. That's equal to P by 2 into I transpose G and I. So this is basically the torque that's coming out of the system, and then we have a P by 2 term here because the mechanical speed is given as the electrical speed divided by the pole pair, that's P by 2. P is the number of poles, and hence the electrical speed divided by the pole pair will give us the mechanical speed. And if you divide the mechanical speed here, P mechanical by omega Rm, what you obtain here is the torque output, that is Te, that's equal to P by 2 into I transpose Z into I. Okay. So this is the expression for the torque, and the expression for the torque will be beneficial for us when we go for the simulation of electric machines. The mechanical output is the torque, and the torque will be leading to the speed. So we have to know the torque output to simulate the entire machine. Okay. So here we have already seen that Te is equal to P by 2 I transpose G and I. So this is the expression for the torque. And if you want to find out the torque expression, we can simplify this equation, and this equation has got the product of the current, the matrix G, and again the current. So we can simplify this equation, P by 2. And what about I transpose? I transpose is IDS, IQS, IDR, and IQR. Now what is the G matrix? G matrix we can write here, and then we have IDS, IQS, IDR, and IQR. Now we can fill up this matrix G, and the matrix G, as we have already seen, has got these elements. These are the elements of matrix G: minus MQ, 0, minus LQR, MD, 0, LDR, 0. So if we simplify this, we will have the expression for the torque. Okay. So we can simplify this, and what we obtain here is the final expression for the torque, that's equal to P by 2 into MD, IDS, IQR, minus MQ, IQS, IDR, plus LDR minus LQR into IDR and IQR. So if we simplify this equation, we get the expression for the torque. Yeah, this is the expression for the torque that we have seen. Now this torque is a very interesting component. This torque is called the reluctance torque, because this component of the torque is coming out due to the variation of inductance between the D axis and Q axis, LDR minus LQR. You can see this particular term. So this is the total expression for the torque for a Cron's primitive machine model. Now in this two lecture that we have already seen that we have introduced the generalized theory of electric machine. Also, we have introduced the concept of the Cron primitive machine model, and we have derived the equation for the voltage and currents and also the equation for the torque. Now, as we have already said, the generalized theory will help us to analyze all machines in a common framework. So, we need some example. So, we will see that how the generalized theory can be used to simulate a simple DC machine in the next lecture. In the next lecture, we will try to take a DC machine model. Using the generalized theory, we will try to simulate the DC machine.